Hello everyone, welcome to week 4 of the tutorial sessions of the nptel course MA29 Introduction to Rings and Fields. So I am Pawan Kumar Aikwade. I will be explaining here some sample problems that will explain you to solve the current assignments and understand the concept better. Okay, so let's start. So suppose you have rings R1, suppose let's say R1 comma R2 are commutative rings rings. There are two cases, maybe with unity or without unity. It doesn't matter. With unity, then you consider the product ring, which is set of all tuples a comma b. A belongs to R1 and B belongs to R2. Okay, this set is uh, forms a ring with following operations. One A comma B plus C comma D will be happen pointwise. Similarly, if you do the multiplication, that will also be pointwise. The multiplication will be in the corresponding rings R1 and R2. Okay. So with these operations given, we know that R1 we have R1 plus R2 is a ring. Okay. Now the question is, how are the ideals look like? Ideals in R1 cross R2. So the proposition is every ideal in R1 cross R2 is of the form I1 cross I2, where I1 comma I2 are ideals in R1 and R2. Okay, forms. Okay, here also I should specify that value of this. Then so forms a commutative ring because your original ring was commutative. Ring. If your given ring was unity, then this is also with unity. Okay, so it depends. Everything depends on the base rings R1 and R2. So this is the proposition that every ideal in the product ring R1 plus R2 is the product of two ideals in R1 and R2. Okay, so let's prove this. So let I, since I is a subset of R1 cross R2, it is of this form. Or I don't have to write this. I is, let I subset of R1 cross R2 be an ideal. Okay, now take I want to be set of all A belongs to R1 such that A such that there exists B belongs to R2 with A comma B belongs to I. Basically, I am collecting all the first components in I. Yeah? That's all. And similarly, I2, if I collect set of all B belongs to R2 such that there exists some A belongs to R1 with the property that A comma B belongs to I. That's all. If I collect things like this, then basically we want to prove that I1 and I2 are ideals. That's all. And I will be I1 plus I2, of course. Then we know I is I1 cross I2. Okay. If you need any shorter proof, okay, let now then we show that a comma b belongs to I. This implies a belongs to I1 and b belongs to I2 because of the proper definitions of how I1 and I2 are defined, and then this will imply a comma b belongs to I1 cross I2. Am I audible right properly? If there is any problem in voice, let me know.
You are audible.
Okay, thank you. So then I get a comma b belongs to I1 cross I2. Now suppose element a comma b belongs to I1 cross I2. Okay. Then what? Question is, and I want to show and claim is a comma b should belongs to I. Right? So what I know is a comma b belongs to I1 cross I2. That is a belongs to I1, which implies there exists, let's say, some c such that a comma c will belongs to I and b belongs to I2 will imply there exists some d such that d comma b belongs to I. Okay. Now what? I need a comma b, right? So I think I need something like a0. Okay. Okay, so this is, let's say, the remaining part that I want to show that I equals to I1 plus I2. But before that, I'll show that I1 cross I2 will be an ideal. Okay, first of all, the elements that I have formed, let's say, let's prove that these are ideals. Okay, so claim is that I1 uh, and I2 are ideals in R1 and R2. How to prove this? Let an element A belongs to I1 and any element R belongs to capital R1. Then what will happen is, by definition, there exists some element B belongs to uh, R2 such that A comma B belongs to I, but then this will imply R times A comma RB belongs to I because I is an ideal, but then by definition this will imply RA belongs to I1, right? And all similarly, I mean, if you take for any, let's say B belongs to I2, okay, and there exists A belongs to R1 such that A comma B will belongs to I, then for any R in R2, right, what do you get? R times A comma B belongs to I which implies RA comma RB belongs to I. But now for this element you have an image, we have a pair, right? RA which is in R1. This implies RB is an element in I2. So I took an element of I2, I took any element R from R2, the product is in I2. This will imply I2 is an ideal. Okay. So what I have is I1 is an ideal, I2 is an ideal. So the only question remained is I same as I1 cross I2, right? Is there any doubt? If how about subrings? Because I1 and I2 has to be subrings also, right? Yeah, I missed this. So before saying ideal, we have to show first that those are the subrings, right? So let A1 comma A2 are the elements in I1, okay? Or let's say A1 comma B1, I'll say. No, A1 comma A2. Which implies there exist elements B1 comma B2 in R2 such that A1 comma B1 is comma A2 comma B2 belongs to I, right? Now what happens to A1 plus A2? So since these are in I, A1 plus A2 comma B1 plus A2 also belongs to I is a subring, but then this will imply naturally A1 plus A2 belongs to I1 and B1 plus B2 belongs to I2. So closed under addition and closed under multiplication by any element from the ring implies I1 and I2 are ideal. Okay, so what I did is I was given an ideal I have decomposed into two ideals I1 and I2. I have showed that I is contained in I1 cross I2. So I just have to show that I1 cross I2 is also contained in I. Okay, so how to do it? So what do I know from here? If C is such that A comma C belongs to I, this implies C also belongs to I2, right? And this will implies D also belongs to I2. Okay, yeah, okay, this is fine. Now what? Okay, I'll restate here. What I want to show is let A comma B belongs to I1 cross I2. Claim is that A the pair A comma B also should belongs to I. This is the claim. So since we have A belongs to I1 and B belongs to I2, implies there exists element C comma D belongs to C belongs to R2 and D belongs to R1 such that C is the pair of A and D is the pair of B. Okay, this belongs to I. This is by definition we got. But again, using the same definition repeatedly, what do you know? Since A comma C is in I, this implies C belongs to I. C belongs to what? I2 and D belongs to I1. right? Because they have the pairs. So and these are ideals. Let's say minus C also belongs to I2 and minus D also belongs to I1. So what do we get? If you have any hints you can give, I am seem to be puzzled for this. How to show I1 cross I2 is contained in I. Basically, this is the logic until now. The only remaining part to show is that I1, this product I1 cross I2 should again belongs to I. How to do it? Just give me 2 minutes. Okay, let's leave this for the moment. So this claim I'll tell you maybe in the next class, that why I equals I1 cross I2. But when this holds, okay. So when this hold, what do you know? Any ideal I can be written as I1 cross I2. It is product of two ideals. Okay. So, I'm sorry for this right now. I think some information is missing. Maybe only maximal ideals are of this form or something like this. I have to check. Okay. So this is a proposition. So we'll have a question based on this. Okay, let's say the question is, let R be the finite non-zero commutative ring with unity. Let R be finite non-zero commutative ring with unity. Let R be finite non-zero commutative ring with unity, then which of the following are true? 1 says any non-zero element of R is either a unit or a zero divisor, and B, there may exist non-zero element which is neither a unit nor a zero divisor. Basically, A and B are like negations of each other. C, you have to show every prime ideal of R is maximal. Okay, so let's see. Option number A, right now you have the ring with R is a finite non-zero commutative ring with unity. Okay, so option A says any non-zero element of R is either a unit or zero divisor. Okay, so let's see how to do it. A, take an element A belongs to a ring R. Okay, so consider the map phi from your ring to ring given as phi of any element x equals to left multiplication by A, simply ax. Okay, so if A is not a zero divisor, then claim is if A is not zero divisor, then A is phi is injective. So let's say if phi of x is same as phi of y for some x comma y, then you have ax is same as ay, then this will imply a times x minus y is 0, but because a is not a zero divisor, this will imply x minus y has to be 0. This implies x equals to y. Right? That means phi is a 1-1 map from R to R, but if phi is a 1-1 map, R is a finite ring, that implies phi is bijective map. Right? Any injective map on finite set is also bijective. Right? This implies phi is a bijective map. This implies the unity belongs to range of phi. This implies there exists an element u belongs to R such that AU is equals to 1. Right? AU is what? Basically phi of u, right? This implies A is a unit. So I started with any non-zero divisors, then I found out that it is a unit. So now I have to show the other way around, that if it is not a unit, then it is zero divisor, something like this. Okay. So conversely, suppose A is not a unit, then 1 does not belongs to range of phi, right? Because if 1 belongs, then you know that A is a unit, right? A times U equals to 1. So since 1 is not in the range of phi, this will imply phi is not surjective, but which is same as phi is not injective, because you have finite rings. But since because phi is not injective, it implies there exist two elements x comma y belongs to R, such that phi of x is same as phi of y. Now if you have this implies ax is same as ay. This implies a times x minus y is 0. So what do you now x comma y says that x is not equal to y. This is what you mean by um, not injectivity, right? So you get distinct elements whose images are same. So but what does this mean? This means A is a zero divisor because its product with a non-zero element is 0. Okay. So we have showed that for any finite commutative ring with unity, any non-zero element is either a unit or a zero divisor. Okay. So part A is done. So what about B? There may exist a non-zero element which is neither a unit nor a zero divisor. We just have proved that this is not possible. Option C, we have to show that every prime ideal is maximal. C, I have to show so in any commutative ring, finite commutative ring with unity, every prime ideal will be maximal. How do you show that? Let be prime ideal. This implies R quotient I is an integral domain that since R is finite, we get R quotient I is finite integral domain, hence a field. So you have an ideal I such that R quotient I is a field. What do you conclude? You conclude I is maximum. So I started with the prime ideal, I have showed it's a maximal ideal. Hence every prime ideal in a finite commutative ring with unity is a maximal ideal. So A is true, B is not true, C is true. Then is there any doubt in this question?
No, sir.
Okay, we'll go for the next question. Question let you have R is set of all functions from set 1 to n to z2. It is a set of all z2 valued functions. Then you know that R is a then R is commutative commutative ring with unity. The operations will be pointwise addition and pointwise multiplication. Then which of the following statements are correct? A, R has a unique maximal ideal. B, every prime ideal is maximal. C, number of prime ideals is 511. And D, every element of R is idempotent. Okay, so basically this R is set of all functions from a set with cardinality 10 to Z2. So we can directly say this is basically isomorphic to, or I mean this is same as Z2 raised to 10, like as we write Rn, R10, something like this. So like 10 tuple, each entry is from Z2. Okay, so proof. R is a um, commutative ring with unity, finite also, because Z2 has only two elements 0 and 1, so this R has the elements 2 raised to R, right? So cardinality of R equals to 2 raised to 10, and R is finite commutative ring with unity. Now from part A, right? No, part C. Every prime ideal of R is maximal ideal. From C of earlier question, we get every ideal of R is maximal. Okay, so which one is true right now? R has every, not every prime ideal. Every prime ideal is maximal. This is true. Then what about R has a unique maximal ideal? Okay, so how many ideals are there in your thing? Uh, yeah. So every prime ideal is maximal. Okay, let's say, is it true? You start with some prime ideal, and let's say if it is maximal. Okay, so let's say define I to be set of all functions, or I'll just take now f belongs to R such that f at 1 equals to f at 2 equals to 0. Okay, this is my not f at, f at 1 and 2, it's 0. Hence, it is easy to verify I is a prime ideal but not maximal, since indeed I is contained in set of all functions which are 0 at 1. This is also an ideal, okay, a proper ideal. Hence I is not a maximal ideal, it is properly contained. Okay, so this is a prime ideal. Okay, hence a maximal ideal also. Oh no, there's a mistake. Yeah. So yeah, this is also maximal. I don't know. This is properly not contained. This is the same. Let's change this. This is f1 equals to 0. I is a prime, hence maximal. Yeah. And then you take another ideal called I2, which is set of all functions which are 0 and 2. Okay. I2 is also prime, and hence maximal ideal. So you have two different maximal ideals, right? That means the statement is wrong, that it has only one maximal unique maximal ideal. This is wrong. So number of prime ideals of R is number of, what is the question, proper or prime? Oh sorry, number of proper they ask. Okay. So yeah, so every element forms an ideal, right? As you know. Now, how many elements are there? 2 raised to 10. So, except 0, you have, except all 1, you have a proper ideal. That means, how many proper ideals will be there? 2 raised to 10 are the total number of elements, minus 1, which is the unity. And each element will create an ideal, and all are proper ideals, right? So, number of proper ideals, 2 raised to 10 minus 1, which is not same as 511, and this is wrong. So every element of R is idempotent. Since Z2 has this property that every element is idempotent, you take any, f belongs to R and do f squared. Right? So what is f squared of x? Which is fx times fx. But this fx belongs to Z2, this belongs to Z2, hence this is also fx, because Z2 has the property that every element are nilpotent. Hence you got f square x equals to fx, which implies f squared is f, hence every element is nilpotent. So this is right. Okay, so go to the next question, and this is,
Sir, please repeat last option. Please repeat.
yeah, okay. See, in Z2, what do you have? In Z2 you have right here 0 and 1, right? So what is the property? 0 times 0 is also again 0, and 1 times 1 is 1, right? So you have the idempotency, right? Any element a squared equals to a, right? For any a belongs to Z2.
Yes. Okay. Okay. Okay.
Yeah,
Okay.
so
Okay.
that's the reason. Now this fx is in Z2, this is in Z2, and if you do multiply it 2 times, you get again the same element. This is the property of Z2.
Done. Done, sir. Done. Done.
Okay, okay. So now your next question. 391. Yes. Okay, so now we'll do maximal ideals in Zn. Okay, just give me a minute. So let your R is the ring Zn, which is basically Z quotient and Z. So, but how do you write this? This is like 0 bar, 1 bar, 2 bar, up to n minus 1 bar, right? This is a ring with operation, right? Addition modulo n and multiplication modulo n, right? As you know. The question is, what are the maximal ideals in Zn? So any ideal is generated by some element, right? Here, every ideal is generated by some element. So how do you find maximal ideal? So I subset of Zn is an ideal only if I is generated by some element A, right? That A belongs to Zn. Oh.